Hey, how you feeling about the homework? You have questions?
Yeah, I'm just not feeling too good. I don't know, I just don't really get this sciencey stuff, and my major hasn't required science in years, and so I just don't think I'm good about it. I just don't get the question. It's the one asking about where a plane would be deflected, and I know it has something to do with the Coriolis Force. I just don't know how that works at all.
All right, so I'd love to help. And you don't have to be a sciencey person to figure this problem out, so don't sell yourself short. So specifically, what on this problem are you confused about?
Well, so we did this experiment in class on the Coriolis Force, and I thought I understood it, but after seeing the experiment, it just made no sense at all.
Okay. So what was the experiment that they showed?
So the professor had threw this ball while it was on a spinning circular surface, and we were trying to throw the ball in a straight path, but it ended up curving.
Okay.
And I know the Coriolis force is an actual force and that it moves things in a straight path, so I just don't get why it turned when we did it in class.
Okay, so this is a great place to start. Let's go ahead and try and define what we know about the Coriolis force.
Okay. So I know it's an actual force that acts on things like wind and water. I know latitude has something to do with it, but I'm not exactly sure what. But yeah, that's pretty much all I know about it.
Okay, so I just want to make sure I'm hearing you right. You know that it occurs at the surface and that latitude plays a part in it.
Mm-hmm.
But you don't get why there's a turning effect and why the ball moved to the right in that example. Am I right?
Yeah,
okay.
Yeah, that's what I'm confused on.
Okay. All right, so not to burst your bubble, but the Coriolis force is an apparent force. So it's not an actual force, not like a push or a pull like I can do with this notebook right here.
Okay.
So rather the Coriolis force, we can just physically see its effect. For instance, do you know why we have days and nights? Okay, so here I'm trying to bridge this gap between the student's prior knowledge with how the Earth rotates about its axis. So as the Earth moves, we know that we block off sunlight from the sun, and then when we have the Earth facing the sun, we have more direct sunlight. So if we can apply this knowledge of the Earth rotating and its axis, we can apply the Coriolis force from her homework problem.
I think so. So we have days and nights because the Earth is spinning, and while it's spinning itself, it's also rotating around the sun. So when it's sunny in one area or day in one area, that means sunlight's reaching it. But when it's dark, that means that there's no sunlight reaching it. So basically that's because of the Earth rotating, right?
Mm-hmm. Yeah, like you said, the Earth is always moving. It's moving about its axis and then also around the sun in an orbit. So since the Earth is always moving, objects aren't always going to look like they're moving straight, but rather they have a turning force. But the turning force we're talking about is just the ground moving beneath us in reference to the actual turning motion.
Okay, that makes sense.
So let's take a look with an example here.
Okay.
I think this might help clear a couple things up. Okay, so what I have here is the Earth, and we're looking down on it. So this point right here is going to represent the North Pole. And so what we're going to try and do is pretend like this is our target here. So we're going to try and throw, for instance, like a ball from that experiment from the North Pole to this dot. And then I'm going to have you hold a pen. And then while I do that, I'm going to turn the notebook.
Okay.
And when I turn the notebook, we're going to see what happens to our motion.
Okay.
So let's go. So what happened?
Oh, wow. So the ball we were trying to throw really was deflected to the right. So that must mean the northern hemisphere deflected to the right.
Right. So let's test it out and see what would happen if this is the southern hemisphere. So I'll mark that SP, meaning South Pole. We're going to use the same type of target again. Okay. And so we hope our ball is going to make it to this target, which is a straight path. But this time I'm going to turn the paper the other way.
Okay.
So now what happened?
Okay, so in this case, the ball was deflected to the left. So that must mean things in the southern hemisphere are deflected to the left, but in the northern hemisphere, it's to the right.
That's exactly right. Okay, so we looked at the paper and we saw the turning motion. Let's try and use an actual globe and see if we can represent that force a little bit better.
So we're starting off at the North Pole, so near Greenland, and then we're going to South America, right? Okay, so if I'm going down there and the Earth is rotating, that means that we ended up all the way in the ocean and completely missed South America.
Bummer.
So if we're starting off in Antarctica and we're trying to go on a straight path to Australia and we add the rotation in, that means that we're going to see a left curvature and end up in Madagascar. Okay.
Wow.
So we saw on the globe when we were trying to throw the ball, if we started in the southern hemisphere and we were trying to throw it to Australia, we saw it deflected to the left. But in the northern hemisphere, we were trying to throw the ball to South America, we saw it deflected to the right. So that must mean because the Earth is spinning about its axis, things in the northern hemisphere go to the right and things in the southern hemisphere go to the left. But what about the equator?
So that's a really good observation. So something we need to think about in terms of the Coriolis force is latitude. So if we look at the equator and we compare it to the latitude of the poles of 90 degrees north and south, we can see that the equator has a lot bigger circumference than the poles do.
Okay.
So if we compare the circumference of the equator with that of the pole, the North Pole, which one has to be moving faster?
The equator, because there's more land and distance there.
Exactly.
Okay. So if a pilot is flying at the equator and just trying to travel in a straight path, he wouldn't have to do as much correcting for the Coriolis force.
Exactly.
But if he were at the North Pole or something, he'd have to factor that in a lot because there's less distance there, causing it to turn more.
Exactly.
Okay, that makes sense.
Okay, yeah, so let's go back and try and revisit the initial confusion we had, and let's work through the homework problem again.
Okay, so the homework problem, is it okay if I use the globe?
Oh, for sure.
Okay. So it had us starting off in New York, and we were trying to get to Egypt. So we're in the northern hemisphere, so I can predict that the plane will end up a little bit further right of Egypt.
Exactly.
So if I start in New York and I'm rotating it and moving towards Egypt, I see that it ends up all the way in South Sudan. So that's...
Does that check out?
Yeah, it does.
Okay.
Which makes sense. So I guess for the homework problem, I would just say it ends up further south and to the right of Egypt.
Perfect.
Okay.
Sounds like you're getting it really, really well.
Perfect. Thank you so much. That helped a lot.
Yay.